Good morning, students. I think you are good at home and keep on studying. As in the previous video, we had studied about how to write the dimensional formula, and we had discussed some of the physical quantities along with its dimensional formula quite in detail, along with its units, and also we had sorted some physical quantities which had similar dimensional formula. Now, today we will discuss about the applications of dimensional analysis. Applications of What are the applications of dimensional analysis in mechanics? Application of dimensional analysis. So today we will study about application of dimensional analysis. First application is to find unit of a given physical quantity. To find unit of a given physical quantity. It is for a given system of unit. For a given system of unit. It is for a given system of unit. For a given system of unit, by the help of dimensional analysis, we find the unit of a given physical quantity for a given system of unit using dimensional analysis. So it is very much easy that writing the definition of physical quantity, we find its dimension. We can easily find its dimension. Dimensional formula can be written by writing the physical quantity on which factors the physical quantity is dependent in terms of its fundamental units, that is MLT. And on the basis of that, we can give its unit also either in CGS system or in SI system. Suppose we are talking about force. As you know that force is equal to mass into acceleration. Force is equal to mass into acceleration. This is the formula for force. Now, in fundamental units, in terms of fundamental units, how can you write it? Mass can be replaced by m and acceleration can be replaced by lt minus 2. So this is the formula for force is mlt minus 2. Force can be dimensional formula for force is mlt minus 2. Now from here we have to write its unit. So can you guess the unit by seeing the dimensional formula? So in CGS system, its formula is what? In CGS system, its formula is gram centimeter per second square. Gram centimeter per second square, which is called as dyne. It is called as dyne. And in SI system, it is called as kg meter per second square, and it is called as Newton. Means if you are knowing the dimensional formula from the dimension, because mass, the CGS unit of mass, we had expressed the physical quantity. We had expressed the physical quantity in terms of fundamental units. In terms of fundamental units, so fundamental units, and there is a defined unit for that fundamental quantity. Mass has gram for CGS, kg for SI. Length has centimeter for CGS, meter for, and time has second in both the cases. So similarly, we can find out the unit also. It is called as Newton. Now, second application is to find dimension of physical constant or coefficient. To find dimension of physical constant or second one, to find dimension of physical constants or coefficients. Second one, to find the dimensions of physical constant or coefficient. So, how can you find the dimension? First of all, I want to explain you what is the meaning of physical constants or coefficients. Suppose you are writing the formula for universal law of gravitation. Universal law of gravitation, that is equal to force is equal to G m1 m2 upon r square. Here G is the constant. So you have to find the dimensional formula for this. Find dimensional formula for this constant. Similarly, in viscosity there is the term viscosity for fluid. Viscosity, in that case viscosity can be coefficient of viscosity. We have to find out the dimensional formula by the use of the formula so used. So first we will try to find out the dimension for gravitational constant. First we find the dimension of gravitational constant. Gravitational constant, that is equal to capital G. Gravitational constant, capital G. There are two approaches. We know that F is equal to G m1 m2 upon r square, and from here we can find out G is equal to F into r square upon m1 into m2, and from here we can write it as, we are knowing the dimensional formula for each and every physical quantity mentioned here. So for force, the dimension formula is mLT minus 2. For distance it is L square. For mass it is m square. Now doing the same thing as I had explained, it is m LQ T minus 2 upon m square. Now it can be written as m minus 1 LQ T minus 2. M minus 1 LQ T minus 2. Clear? The second approach can also be adopted. The second approach is from the relation between capital G and small g. The relation between capital G and small g is Z is equal to Zm upon R square. And from here we can find the value of we can find the dimensional formula for G in the similar way. And now after that we will verify that whatever the dimensional formula for capital G we had calculated in the previous case, there should be must the same dimensional formula in this case also. So it is equal to Z into R square upon capital M, and it is equal to L T minus 2 into L square upon M, and from here you can write it as M minus 1 L cube L square L cube T minus 2 M minus 1 L cube T minus 2, and the SI unit is meter square. Now you can write the SI unit also. SI SI unit for this is meter cube per kg second square. Meter cube per kg second square. Very good. Meter cube, both are minus 1, so minus 1. For understanding you can write it is like that. L cube M T square. Meter cube, this is meter cube, this is kg, and this is second square. So from that we can find here this formula. Meter cube per kg second square. Now second is Planck's constant. Second one is Planck's constant, and we will find the dimensional formula for Planck's constant in three approaches. One by one we are going to discuss. Planck's constant is equal to h nu. Planck's quantum theory, you are knowing that. From there we had seen about the Planck's constant h. About Planck's constant you will study in the higher classes. In class 12 you will study Planck's constant in photoelectric effect. Planck's constant. Planck's constant, and it is denoted by h. Planck's constant denoted by h. From the first approach, you are knowing that E is equal to h into nu, or h is equal to E upon nu, or h is equal to energy you are knowing ml square t minus 2, ml square t minus 2, and frequency that is equal to t minus 1, that is equal to t minus 1. And from here you can find out the dimensional formula for h as m l square. It will go in numerator, then become positive, then it becomes t minus m l square t minus 1. The second approach second approach lambda is equal to h upon mv, and from here we can say that h is equal to lambda into mv. Very good. So from here the dimensional formula for h: wavelength lambda l, mass m, and v is the velocity lt minus 1. And from here we can write its dimensional formula as h is equal to m l square t minus 1. The same dimensional formula. And angular momentum, the third approach is from angular momentum. nh upon 2 pi, Bohr's postulate. In that Bohr's postulate, the angular momentum for orbiting electron is proportional to, is equal to nh upon 2 pi. From that we can calculate the dimension of Planck's constant. Bohr's second postulate, that is angular momentum is equal to nh upon 2 pi, and h is equal to 2 pi upon n into angular momentum. And h has the dimension of angular momentum, Planck's constant, because 2 pi and n are dimensionless quantities. So h has dimension, and it is equal to ml square t minus 1. ml square t minus 1. SI unit of Planck's constant. Now SI unit of Planck's constant. SI, since it has dimension, then obviously it has units also. So its SI unit is kg meter square per second. kg meter square per second. kg meter square per second, or it can be written as kg meter square per second into second, and this is what joule. This is equal to joule into second. Joule into second. Kg meter square second. Kg meter square second square. We had multiplied one second in denominator, so we had divided 1 second in denominator, so we had multiplied 1 second in the numerator, and it will give kg meter square per second square joule into second. Now these are the constants. Now third one is coefficient of viscosity. Third one is coefficient of viscosity. Coefficient of viscosity. Coefficient of viscosity. This thing we will study in fluid mechanics, and coefficient of viscosity is calculated for fluids, any fluid like air, turbine valve, water, each and every head. It is just like friction in fluid. It is just like friction in fluid. So here also we are adopting 3 approaches to find the first approach. And the first approach is from the Newton's law, F is equal to eta A dV upon dy. This is Newton's law, and from here we can find the value of coefficient of viscosity. So eta is equal to F upon A into dV upon dy. Rate of change of velocity, that is dV upon dy. Now dimensional formula for eta. Force mLT minus 2. Area L square, and velocity and distance that is equal to LT minus 1 upon L. Look at here the velocity, rate of velocity gradient. This is not rate, this is velocity gradient, change of velocity with distance. So change in velocity with distance, so LT minus 1 upon L. Now solve it, you will get the dimensional formula. After solving, you will get the dimensional formula as m L minus 1 T minus 1. M L minus 1 T minus 1. So from Newton's, this formula is called as Newton's law. This is Newton's formula for viscosity. Newton's formula, later on you will study. Newton's law, Newton's formula for viscosity. The second is Stokes law. The second approach is Stokes law. Stokes law. All this law you will study in fluid mechanics. So from Stokes law, F is equal to 6 pi eta RV. 6 pi eta RV. And from here you can calculate the value of eta is equal to F upon 6 pi RV. And putting the values for the physical quantities, m L T minus 2, 6 pi is constant, it is the ratio, so it is dimensionless, L T minus 1. And from here you will get the value m L T minus 2 upon L square T minus 1. And from here you will get m L minus 1 T minus 1. M L minus 1 T minus 1. So from all these, from Stokes law also, you had find the formula for coefficient of viscosity. Now the last approach is, third approach is Poiseuille equation. Poiseuille equation.